Okay, so now we're going to take a look back at a piece of the polarization that we did not really explicitly consider for a while, which is the fields. We thought of the response functions. Remember how this worked? It was the integrals, right? The integrals with this product of all these fields evaluated at different times, and then the response function, the S, which was the expectation value. So what we're going to do is look back now at the fields. So I can write down the field part like this. Okay, so we have this product of all these fields. And what you should think of this as is a convolution of the electric fields and the response function. That's the formal mathematical term. A lot of times we will pretend or hope or just postulate that we can represent these fields as delta functions, especially if we do experiments in the time domain. If we do that, then we can pretend that we're evaluating essentially the response function directly in our experiments. In practice, of course, real pulses have finite time durations, in which case they aren't delta functions. But you can include those effects, and there's in the field of different and there are research studies on what are the effects of different imperfections of your pulses on, for example, multidimensional spectra or palm probe responses and so on. All right, so what we're going to do though is take the opposite view. Instead of having a delta function in time, we're going to consider a CW, or a continuous wave field. So CW is just a jargon, but what it means is, like, you can think of this like a sine wave. All right. What else do we need to remember? We need to remember that electric fields are fields. They have a definition in space, not just in time. So an electric field is going to be a function of, let's call this the electric field, the jth electric field. We might want to label them, you'll see why. And then it has a spatial component, which we can represent with a vector r, and a time parameter. Okay? And one parameterization would be something like this, like an amplitude, and then a phase. And then I just want to make sure I get my, yep. We'll tell what all these terms are in a minute. So you'll notice as I'm writing this that the first term and the second term are complex conjugates of each other. And what does that tell us? It tells us that the time domain representation of the field is real. Okay, in other words, an electric field in the time domain is an observable. We can measure it. All right, and there are ways of measuring that. In fact, it's important that we can measure the field. It's one of the things that allows us to do various kinds of optical spectroscopy methods. Sometimes you don't measure the field. Sometimes you just measure the intensity. And there's nothing wrong with that, but it limits what you're able to do. When you can measure the field, you have more possibilities of spectroscopic methods. So what we'll do is assume that we have a plane wave, which is to say that we have, basically planar phase fronts. And so from that, we will have means that a planar wave with a constant amplitude in time, meaning CW, not constant amplitude, but a constant amplitude term here. The phase obviously will vary because it's going to have an oscillatory amplitude. Right? So we're going to fix this term, which this could have been something like a pulse, right? A of j, for example, could have been something that looks like this. That's how you can put pulses back in. All right, so if we make it just a magnitude, then we have the modulus squared over 2, right? This is this, and we're looking at the compass conjugate of it. And so then we have now e to the I k r it's k dot r. If you forget the dot, that's okay. We will be using the spatial wave vector component for sure, because that's what allows us to spatially select different signals that we want to measure. Okay, well, if you look at this, this looks like 1/2 times e to the i's theta plus e to the minus I theta, right? Where theta would be like k dot r minus omega jt. Then that means this is a cosine. So we have a, and then we have cosine k dot r minus omega. Okay, I'm forgetting the j's all over the place. All right, so we have that. Now what we're going to do is we're just going to consider a place, a reference plane, if you will, for any number of the fields that we're considering, shooting at our sample. So once we choose a reference plane for our plane wave, then k dot r will become a constant. And we'll see what's significant about that in a minute. So that means that we can kind of ignore the spatial wave vector part and consider just the temporal part. And that's sort of what I want to get at first. All right, so then that allows us to consider a field as like cosine omega j t. That's the easiest way. Okay, there's a magnitude, but we don't really care so much about the magnitude. Why did I switch from minus omega to plus omega? Because cosine's an even function and you can do that. Okay, so now what we're going to do is we're going to realize that what's happening in our experiment is that we're kind of going to be multiplying lots of fields by each other. Okay, and so we want to see what is the consequence of multiplying lots of fields by each other. And the interpretation of this is relatively straightforward. The idea is that when you have light, right, once you know the frequency of the light, from the Planck relationship, we know that this frequency is equal to the energy divided by h bar. And that frequency is constant. If I take that frequency, if I take that light and I put it into a material, the material might have an index of refraction, which even a vacuum has an index of refraction, it just happens to be equal to 1. So it's going to have an index of refraction of n. And that tells me how the phase velocity changes. So how do the crests of the wave change as a function of time? And then from all properties of waves, the wavelength of a wave times its linear frequency, so I'm writing it now as a nu instead of omega, is equal to c, the speed of the wave. This is true for all waves, not just light waves. But what's unusual about light waves is the energy of the light wave is fixed, and it fixes the frequency. All right? So what that means is that you have the wavelength equal to c over nu. But this c here is the speed of light in the vacuum. That's not the speed that the light travels in a medium that you might have. So if we want to be really careful, we're going to put a naught here. It's lambda naught. That's the wavelength in the vacuum. If you have a material, then the speed of light becomes different. It's c over n. Okay, so that means that when we now compute the wavelength, it's not lambda naught anymore. I shouldn't have put that there. I got carried away. This is equal to c over n times nu. So what does that mean? N, for all normal materials that you're likely to encounter, is greater than 1. Well, since the index of a light is going to travel slower in typical media that aren't weird or inverted or something like that. So light's going to travel slower. And so what that means is when n gets larger, what happens to the wavelength? It goes down. All right? What that means is that if I have light going along in the vacuum, and I compare it to the same light, but now I put a material here, the wavelength is going to get smaller, right? Because this number gets larger, so that wavelength gets smaller. That's obviously highly exaggerated. And then as soon as it leaves again, it turns back to the normal wavelength that it had. So it's a little bit like an accordion. You smush it, the little accordion ridges get closer together. So the medium that you put here is going to cause a light wavelength to be shorter when it's going through, and that when it gets out, depending on how far it's gone through and how much it gets shorter, the phase of the light wave will be different than the phase was of the light that didn't go through, or coincidentally, maybe it's the same, whatever it is. That's why we have phase delays when we have something going through one medium and something going through another medium. Okay, so everything I just told you takes the sort of textbook view about light. Light has the frequency. Once you know the frequency, you know the energy doesn't change. But what we know is that that's only the case if the light doesn't interact with itself or any other fields. So what nonlinear optics allows you to do is allows you to have an optical response, okay, which enables the field to multiply itself, n times. So if a linear optics, you'll have one field. The frequency will be the same as the one that you applied. But when you have two fields, now all of a sudden you can allow the light essentially to interact with itself. It's not going to do that without a medium. Okay, so what's interesting about this then is this means that if we have nth order spectroscopy, and we know we're going to have the product of fields, then we should think about what happens if we just ignore the complexities of the response function, just assume it's like a uniform response, it doesn't depend on frequency in any way. Then what we can do is we can say, I get it. I'm going to have cosine omega 1 times time times cosine, whoops, that's not right. Times cosine omega 2 and dot, 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 all the way up to cosine omega n. Okay, and what this allows us to do is to think about what happens when we multiply, for example, cosines by each other. So if I have cosine, and you can, then this is why I warned you that you might want to dust off your trigonometric identities. So if I have, for example, cosine A times cosine B, this is equal to 1/2 cosine A plus B plus cosine A minus B. Okay, and notice, of course, that since cosine is even, whether A or B is bigger or smaller doesn't matter. We can switch the order of these two things, and the cosine is the same. It also tells us that if A and B are the same, then this second term goes away, and we only have the second harmonic, what you would call it, the second harmonic of the light, because the difference frequency is 0. Now, this is something that we want to think about. It's not always going to be the case that we have a single frequency, cosine A and B, because we might have a pulse. And when we have a pulse of light, we're going to have a bandwidth of frequencies. And because we have a bandwidth of frequencies, there could still be a difference frequency, even if your pulse is tuned more or less at the same wavelength, because there'll be the high frequency part of your pulse can interact with the low frequency part of your pulse and cause the difference between the two. That becomes especially important, for example, in a kind of spectroscopy called impulsive Raman scattering, or impulsive stimulated Raman. Okay, so now I can keep doing this too. I could keep going to adding a third one, right? So if I add a third one, then it gets a little bit complicated, but what you'll see is I'll do the third one because it's important for our third order response, which is where we're stopping, right? Because you can do this forever if you want. So you have cosine A, B, and C. So that would simply mean that we multiply the whole thing by cosine C. That means that we'll have the sum, A plus B plus C, the difference, A plus B minus C, the sum, A minus B plus C, and the difference, A minus B minus C. Right? So we write that out, and you get this factor of 4. This ends up being cosine A plus B plus C plus cosine minus A minus B plus C And again, we could switch around the order if we don't like it, because you can multiply these by -1 without changing any of the values because of the fact that cosine is even. Cosine A minus B plus C plus cosine minus A, oops, plus B plus C. Okay, and what you can see then is we have A plus B plus C. That's going to be, then that means the frequency we get out is going to be the sum of all three of those. So that's an example of some frequency generation when you have three fields interacting. I should have pointed out that when you only have two fields interacting, you can also get the sum frequency generation. So this is the nature of why we have things like SFG spectroscopy. You can take two fields, say one infrared and one visible, make them interact with a material, and we'll talk about the nature of the details of how that works. And then the emitted field will be the product of those two input fields, and it will be the sum of them. This again is the difference, and that's one way, for example, of making a vibrational coherence by the Raman effect. Here we have what would be perhaps some frequency generation with three fields, or if all fields are the same, that's usually called third harmonic generation. And then there's a case where you subtract two of the fields from one. Here we're adding 2 to 1, and we're adding 2 to 1. Okay, and so then what's going to end up happening is these frequencies are going to be, could be potentially quite close to the initial frequency that you generate. And so these three are going to be the three terms that are significant when we consider the typical third order spectroscopy that many chemists do, like pump probe spectroscopy and two-dimensional spectroscopy. All right, so hopefully you can start to see now where the fields part is coming in. We worked hard to at least list what the material response function is. And what we'd like to do next is to work out sort of what can we learn about the going back to the directions, right? So just so we can, and so one thing that you can notice from this is there's a pattern, and we write the pattern down, and that'll be the end of this one, that we can have a signal frequency for an nth order process. It's going to have all possible frequencies, plus or minus omega 1, plus or minus omega 2, plus or minus omega n. Okay, so what that tells us is there's going to be two different potential, values for each of these. And so you should be able to figure out then that tells us how many total frequencies we can get out. So some of those frequencies might be similar to each other. For example, if all the omegas were the same, then that'll make a high amount of symmetry. If the frequencies are different from each other, then we'll have quite a bit of different frequencies that we can measure. All right, and so those are all the possible combinations of frequencies that our signal can have. What we're also going to find out, I haven't done it yet, well, this should be a J. What we will find out is that the signal field direction has exactly the same pattern, because what's so special about omega up here? Nothing. K does the same thing. So we're going to have a similar feature with the directions. And what that tells us is that if we use beams that aren't pointing all in the same direction, or not all coming from the same direction, but of course they end up at the same spot where the sample is, that's going to mean that there's going to be different signals going in different directions. So not only can we tune our detector to measure the frequency we want, we can also move it in physical space so that it sees the signal that we're trying to measure, right? So this turns out to be really convenient, because if you're doing, let's say, some frequency generation spectroscopy, you know the frequency of one field, and its direction, you know the frequency and direction of the other field, your new signal is going to come out in a different direction. So you just put your detector there. And even if you don't have a spectrometer, you can still just measure the whole intensity, and you can be pretty sure that you're going to be measuring the pathway that you're aiming for. All right, so this is quite useful in what we call non-collinear geometries. These different wave vectors are proportional to momentum. H bar k is momentum for light. So you can write momentum equals h bar k. And so when we think of this as momentum conservation, the field directions add up to another direction such that there's no loss of momentum. So momentum conservation is this. The product of the fields giving out the other field is an example of energy conservation. So by conserving energy and momentum, which most mechanical systems should do, we arrive at these two conditions between what signal frequency we can get and what signal wave vector we can get. We'll talk more about wave vectors with some specific examples. This, by the way, this connection of the direction has a jargon, and the jargon is to say phase matching. We can talk a little bit more about what phase matching means. It was discovered at the University of Michigan by an undergrad, and it's a nice long story that goes back to the very earliest days of the laser. And now, of course, we use it all around the world, all the time, whether we know it or not, many times.